Well, let's start our examination of relativity and light with a flashback teaser. Imagine you and Sky King are flying in the Songbird, and you have a Red Ryder BB gun with you. You know that you're flying at 150 miles per hour, and you also know that when you fire your rifle at the target range, the bullet leaves the muzzle at only 100 miles per hour. So the plane flies faster than the bullet. Now you point the rifle in the same direction that you're flying and pull the trigger. What happens? Does the bullet ever leave the muzzle? Since you're flying at 150 miles per hour and the bullet only travels at 100?
A fun question, but an easy one. Sure it does. The bullet's speed from the rifle gets added to the plane's speed, and the bullet takes off at 250 miles per hour. Reason it out this way. The bullet is moving at 150 miles per hour just sitting in the gun, since it is moving along with you and Sky King and the Songbird. Then when you fire the gun, the bullet is blasted forward at an additional 100 miles per hour. So it leaves the muzzle at 250 miles per hour relative to the ground, 100 miles per hour relative to you, Sky King, and the Songbird. This is classical relativity. Simply add the velocities.
Okay, but now suppose you're with Snoopy in his Sopwith Camel, and you know that on the ground, light from your flashlight travels at 186,000 miles per second. Now from the plane, you point the flashlight forward and turn on the beam. Does the light travel forward at 186,000 miles per second plus the speed of the plane?
I know the answer, but I don't understand it. If that's what you're going to talk about today, I can't wait. Preach away, my hero.
Okay, here we go. Jeeves?
The example of adding velocities, in the bullet and plane example, is classical relativity at its finest. This classical version of relativity, simply adding the velocities, worked perfectly well for centuries for describing horse carts and ships, or baseballs and trucks, even airplanes, and rockets and bullets. But the relativity of classical physics is merely a very close approximation to reality. At very, very fast speeds, classical relativity breaks down. But this wouldn't be clear until scientists began flying Sopwith camels and examining the nature of the fastest known thing, light. In the middle of the 19th century, it had been known for quite some time that electricity could be used to make a magnet, and that magnets could be used to make electricity. But the man who made the first color photograph, James Clerk Maxwell, unified everything known about electricity and magnetism in 4 magnificent equations. And these equations described an electromagnetic wave that would travel through the empty space at exactly the measured speed of light. And in fact, this wave was light. According to Maxwell, light was an electromagnetic wave that moved through empty space with a speed of 186,000 miles per second. But from the standpoint of relativity, the question naturally arises, relative to what? The equation seemed to say that light moved at 186,000 miles per second, relative to everything. This was a dilemma facing the physicists at the turn of the 20th century. If Maxwell was right, then light moves with a velocity of c, 186,000 miles per second, always. But if classical relativity was right, there is no absolute velocities, and the velocity of light should depend on who is doing the measuring and their motion relative to the source of the light. How could both be right? Either our understanding of motion or our understanding of electromagnetism and light were in jeopardy. The very foundation of physics was facing a crisis. A 26-year-old patent clerk named Albert Einstein would provide the way out of this crisis. Einstein accepted both of these seemingly contradictory notions and changed the course of science. He accepted the idea of relative motion, but restated it as follows. Any person moving at a constant velocity will observe the same laws of physics that a stationary person observes. And since the speed of light is part of the laws of physics, Einstein postulated that all observers will measure the same speed of light, regardless of their state of motion. But speed is just a measure of distance moved in a given time. And in order to agree on the speed of light, different observers might have to disagree about distance and time.
Okay, I think I'm getting it. If we have to agree on velocity, then we might have to disagree on the components of velocity?
Absolutely true.